I'd like to welcome everyone today. My name is Rick Dye. I'm the Key Account Manager for Flow Meter Products from Teledyne ISCO. We like to say we have a record crowd today. We're very excited about that. A lot of new faces or new names on the list and a lot of repeats. So I'd like to welcome those that have attended before back, and then the new ones. Thank you for attending. So I think we have an exciting presentation today, and if you have any questions, please feel free to use the chat feature on your browser there, and let's go ahead and we can, on the WebEx thing, and we'll answer those at the end of the presentation. And if we don't answer them then, we'll go ahead and answer by email. So today's presentation, we're going to talk about how to monitor your collection system wastewater flows. What I'm going to do is talk briefly about some of the background of why we do collection system monitoring. We will go into the technology in more detail of the different types of flow technologies, the applications that they're used in, and some things at the end to hopefully help address and answer some of the questions you might have. Typical wastewater treatment system, you have your industrial dischargers, your municipal dischargers. We go to a wastewater plant, and we all know how that ends up. It ends up in the water, or receiving waters. So we want to make sure we do a good job of treating the wastewater. This is kind of just a little graphic of a basic wastewater system. You have a business or industry that is discharging to a local main sewer line. You have residential discharge as well. They go into more of a larger trunk line and ends up in the wastewater treatment plant. We're going to talk about some different types of sewers today and some of the things that we do with those and how they're used. First one is combined sewer system. This is one of the older systems. Basically, in the old days, water left the house and it went right into the receiving waters. They came up with a combined sewer that would divert water from the receiving waters to the treatment plant, unless you had enough of an overflow that would cause it to, again, overflow into the lake or river. We went from there to separated sewer systems. So most of the newer systems that you see today are separate. You have your storm drain, storm sewer that's separate from your wastewater sewer lines. So any municipality out there is striving to do a couple things. One, deliver a high level of service to their customers. Want to make sure they do the best they can for the customers. Maintain regulatory compliance at all times. Do not want to violate any laws. Improve their asset management. Utilize what they have and make sure they do the best job with that. Want to develop a more efficient and productive work management plan. We want to use what we have to the best of their ability. The challenges that a lot of people are faced with, the economy these days prevents people from hiring a lot of times, additional staff and equipment. So but despite that, you don't get a mulligan against your permit requirements. You still have to do what your permit requires. And really, like everyone else, whatever business you're in or what industry, you're doing a lot more with less. And that's true today as more than ever before. Problems also with fewer resources are going to increase in frequency and intensity. And if you don't have the resources, it's tough to do some of the preventive maintenance to prevent these things from happening. So let's get behind these problems. And one of the reasons we want to do that, we don't have the resources we have to rectify some of these problems. We have an aging infrastructure and aging assets. A lot of things are getting up there in the years, wearing out, and so on. Regulatory requirements are not getting any less. They are continuing to increase. And there's a lot more with the internet and things like that. We see a lot more awareness of citizens knowing what's going on out there and being more proactive on their environment. We also see an increase in I&I because, again, of the increase in people as far as population goes. And the more of those that happen, the more aware people are, the more painful they are for everybody involved. So some of the indicators and how people are judged on the system performance, really how well does your system respond following a storm event? What is the response time? How long does it take to get back to normal? How many complaints are your customers filing? How many lawsuits? Things like that. Number of blockages in your lines due to grease and possibly pump station failures. The number and volume of unpermitted discharges, and those would be like SSO, sanitary sewer overflow. What is the effect on the operation of your treatment plant? We all know when you have a high INI event, your treatment plant does not work nearly as effectively as it should. Okay, so where are we going to start? Well, we want to develop some sort of an overall strategy to combat all these things. Normally, you'll conduct some sort of an internal audit to really assess what are your competencies and capabilities, what are your staffing, how many people do you have, what do you have for equipment, and so on. Be able to identify, again, who else might be available to assist in addressing some of these problems. Maybe you need to go to a consultant or some professional outside help when needed. The bottom line is you need to begin to know your system. And one of the ways people start out, they look at a Plat Map and they decide, okay, I have areas of town that I know I have more problems. They'll break them up into basins or sub-basins, and they try to break it out that way to get just an idea of where to even start. They'll then look at their wastewater collection system. They'll break that up as well into, well, we have pump stations, we have storm sewers, we have our residential area, and so on, as well as industry. So where do I have my biggest problems, and what am I going to address first? So one of the first things people will do is they will look at flow measurement. And really, flow measurement is just a key to understanding your collection system. Without an accurate flow measurement system, you're going to have a really difficult time getting a handle on it. There's a lot of different technologies in the marketplace to choose from, so you need to make sure you get the right one for what you're trying to accomplish. You're going to do a lot of surveys and studies to figure out where you're going to go and then what technology best applies at that location. Sometimes you're going to need multiple technologies to be able to handle all these different site-specific variables that you're going to encounter. Okay, so let's talk flow monitoring. Why? Typically, people do INI studies with flow monitoring. INI is inflow and infiltration. We're looking for what happens when it rains. CMOM is one of the buzzwords you may have heard in the past, capacity management, operation, maintenance, basically holding the municipality more accountable for what's happening in their collection system. We have a lot of stormwater monitoring activity, which involves samplers and rainfall measurement. Combined sewers, which is a permitted way of discharging. Those are being slowly but surely phased out as well. Billing applications. We see a lot of billing applications. Normally, you'll see a billing application, at least in the past, using a primary device, such as a weir or a flume. Area velocity is one of the methods that you can use when you do not have a primary device, and we're seeing more and more of that, especially with the introduction of laser technology. Custody transfer. I'm billing one municipality for treating their water. There's also a lot of water rights stuff, especially when you see the drought in California and the West Coast. We have water treatment and water rights. And really, it's all about demonstrating that you are trying your best to comply and improve the system. Here is the dream location. We have a house that has a sanitary line that goes to the sanitary sewer. We have a storm catch basin that catches the storm sewer, and everything is sealed, it's tight, there's no leaks, and everybody's happy. We all know that's not really exactly the way it works, but that's the goal. Inflow and infiltration really is one of the most problematic things that public works departments are facing these days. A lot of communities have older infrastructures, and they have repeat violations. So some of the newer municipalities have newer infrastructure. They don't see this as much, but a lot of the older ones have a lot of problems. And we normally see a lot of this with areas with high annual rainfall. Having said that, I do have customers in the desert where you don't see a lot of rainfall, but they're as interested because when it does rain, they want to make sure their infrastructure is able to handle it, and they're also interested in when there's no flow, what's going on there. So interesting, different kind of concepts. Typical INI sources, normally cracked, broken pipes. We have roots that intrude into the lines. We have root drains and or vents and drains from some of the older structures. different types of manhole covers leak. We have some CSOs that are tied into some of the regular lines, illegal sewer service, sump pumps, etc. This kind of gives you a little better idea of some of the sources of inflow and infiltration. Again, a number of things that I just mentioned. Obvious problems, health risk, property damage. Again, it's going to render your treatment plant less efficient, less effective, and it's going to use up some of the capacity. So if you want to expand an area of your town and you want to add a housing area or something, you may not be able to do it because you can't handle the amount of water, especially when it rains. So there's different tools in addition to flow, but I'll talk about some of these other ones that you can use in order to identify and figure out where your I&I might be coming from. First one, though, you're going to use primarily would be flow measurement. You want to know what's going on, and flow is the best way to find that out. Once you've identified flow, then a lot of times you'll do CCTV camera work. So we'll run cameras through the sewers. They'll do smoke testing as well. One thing to note, though, these are not very practical 24/7 day-to-day monitoring practices because of obvious reasons. Flow monitoring does allow you to do more continuous permanent monitoring, but these are certainly a great way, once you've identified an area, to go in and really fine-tune your monitoring. The key with all this is you're looking for the I&I. We have our purple line here, which is our rain event or wet flow. Yellow is our dry, and the red is the I&I related flow. Without going into too much detail, this is the goal of any monitoring program, is to be able to overlay rainfall. In this case, we had 1.68 inches with 8.2 million gallons. So your software needs to be capable of doing that as well. SSOs are sanitary sewer overflows. These are unpermitted discharges. So we will have a lot of times blockages, things that happen, a lot of times related to lift stations that aren't working properly, might have grease plugs and so on that aren't allowing the water to go through, and you get a backup. So SSOs are obviously a major problem. But let's talk about combined sewers a little bit. This is a pretty good description of what we're doing with combined sewers. Again, we have our normal flow coming into the structure, but we have a control device or a diversion structure that will deflect that water to the wastewater treatment plant. We have a high level of water or high flow due to rain. It will overflow that CSO line. Most cities with CSOs are attempting to remove or completely eliminate those. In some cases, that's very difficult to do. The CSO, some of the oldest collection systems are some of the oldest collection systems. Again, we're diverting wastewater to the treatment plant. We only send water to the wastewater to the receiving waters when we exceeded the diversion structure. One of the challenges, though, is a lot of these are typically very large pipes and have very low daily flows. So how do you accurately measure that? And that was always a challenge. You could put a high accuracy large pipe device in, but how do you measure your low flow? We'll talk about that here in a minute. But most times they were just required to report the length of time that they had an overflow and estimate the amount of flow that went out. Billing applications, again, custody transfer, outlier communities discharging to municipal wastewater plants. We see this more and more. Accuracy is key. They want to make sure they're billing the right amount, and the communities want to make sure they're paying their fair amount as well. It needs to be defensible data. One thing you'll notice with all ISCO flow meters, we are very keen on defending the data. All of our meters have diagnostics capability that helps support the readings that we're giving you. Hydraulic modeling is another one that's a big deal. This helps predict the impact of a storm on a collection system, and calibration of the hydraulic model is only going to be as good as the data going into it. So I look at the Weather Channel all the time, especially being in Nebraska, and I hear them talk about the models. They're very good at predicting, for the most part, some of the storms. Well, hydraulic modeling in a sewer system is the same way. If you have bad data, you're going to get some bad results. Multiple applications, you're going to see a lot of things in hydraulic modeling. Maybe I have large pipes, maybe I have pump stations and so on. So you might need a variety of different types of technologies. Again, the application is key. Not every meter is going to work, no matter how good the meter is, in a bad location. So you want to make sure you verify the application before you get to to putting in equipment or specifying equipment. Where are we going to begin? Again, we want to assess the collection. We're going to start with flow monitoring. We need to know really what technology we think we should use. What resources do we have? Do we have the personnel to be able to install meters? What is our funding? How much budget money do we have? Where are we looking? A lot of times GIS mapping is a key component there, as well as, again, consulting engineering firms to help people get started. And a lot of times that begins with a flow control master plan. Okay, one of the things that I think we do a pretty good job of is providing the right product for the application. That's the reason we supply so many different types of flow products. Our sales reps in the industry are second to none in diagnosing your application. We also have people internally that can help you do that. So we think we do a good job of giving you what we think will be the best results for you. Some of the equipment options we're going to talk about today, one will be the signature flow meter on the bottom left. The other one will be the 2100 series on the top right. So just a real quick overview of Signature. What Signature is designed to do is be a smart device. It can handle multiple inputs and also has multiple outputs on a single platform. It uses what's called a TiNet teledynamic environmental network to communicate to multiple sensors. Technically, it can handle 9 teledynamic environmental network smart sensors. The other key thing is it can also interface with non-ISCO devices. If I have Modbus output of a mag meter from some other location, we can input that as well as SDI 12. So a lot of flexibility in this, both in and out, and we'll talk about that in a little bit, but that's the Signature flow meter. 2100 series, many of you are familiar with this. We have been a very big hit in the market and in the industry. It came out in the late 90s, and it was designed to be a modular system. It was our first modular approach. We went with a waterproof NEMA 6P rated design. Can be either portable or permanent. You can have multiple modules and different types of sensor technologies. So in this case, we can use an ultrasonic. So if I have a basic SSO line where I just want to know if I have an overflow, we can use a 2110, which is a ultrasonic module. If I want to do more area velocity, I can do a 2150. And if I want to do laser, I can do a 2160. So a lot of flexibility there as well as redundancy in the system. Some of the flow meters you may have seen in the past, the one on the left is a 4200, more of an industrial monitoring device. The one on the right is a flow logger. So things have came a long way since that time. So let me bring you back to Flow Monitoring 101. Before we had all these wonderful devices, there was the Manning formula. Manning was a method by just taking the level measurement. We would know the slope, we could estimate the slope, roughness coefficient, and calculate the flow. It worked okay under perfect conditions. However, as we all know in the industry, there's very few perfect conditions out there. When you're looking for I&I, submerged flow situations and things like that, you are not going to probably get very good results. And weirs and flumes were not very practical in those types of applications as well. So along came area velocity flow measurement. Q is my flow is equal to the area of the wetted perimeter. Normally that is done using a level measurement, either a pressure sensor or an ultrasonic level sensor. Velocity is the V component and normally is done using a Doppler method. Can be either a contact or a non-contact sensor in the case of laser flow. This is what the 2150 module looks like. The sensor obviously is on the right. It can read down to 1 inch. And the way this works is you have a sensor that's in the pipe mounted on a ring. It measures the water depth using a pressure sensor, microprocessor-based pressure, I should add, very stable. We transmit a known frequency into the flow, and we get a frequency shift of what's coming back at the sensor, similar to a police radar gun. We will trim off the front end, back end of that, and what's left we will do a weighted average of. This is known as a continuous wave velocity measurement, and it's a very, very decent way of doing it. This is showing kind of how you can add to the system. It's very easy to stack modules, and the rings are in the background there. You can see those are stainless steel rings. They can also be, in some cases, inserted from above ground. We use normal off-the-shelf alkaline lantern batteries, so they're battery-powered systems, waterproof for the most part, battery-powered, and away you go. This just to kind of show you all batteries are not created equal no matter what equipment you're using. You want to make sure you get the right battery. We recommend Energizer 529 or Rayovac 808, but you can use any of them as long as you know that you're not going to have the battery life. Okay, so a wrap up of continuous wave Doppler, and I'm going to talk about advantages, disadvantages of each technology that I'm going to discuss today. The advantage works well in depths typically lower than 24 inches. Doesn't mean you can't put it in a pipe that's going to go 10 feet deep. It will read that. But any continuous wave sensor has a certain range that will be effective. And over the years, we've learned where that is. And we will be in the 5% range, normally within 24-inch depth of water. When it gets deeper than that, you're going to decrease in some of your velocity accuracy, which is common with any continuous wave sensor. The reason is it's a shotgun pattern. It's transmitting out, the signal's getting more and more scattered the further and the deeper the flow gets. But it is a very good approximation of fluid velocity. Low power consumption device wakes up, takes readings, goes back to sleep. It's also very portable, and it's also quite low cost. So it's a portable way of putting an army of meters out there. So what are the disadvantages? Well, you have a sensor that's in the water. You have debris potential issues, rags, damage to sensors. You periodically want to check calibration. And because it is a shotgun pattern, your velocity accuracy will decline a little bit as you get larger than 24-inch pipes. For that reason, we see a lot of these in some of the smaller pipes. So that is continuous wave Doppler. Now I'm going to talk about acoustic Doppler, or what's called range-gated Doppler. And what range-gated Doppler is a sensor that is able to profile up into the water column and get multiple discrete velocity components. What we have that provides this is a new device that we just released called the AccuPulse. AccuPulse has two sensor designs. One is what's called a deep water, and the other one is a shallow water ADFM, or acoustic Doppler flow meter. So single electronics, but multiple sensors. The AccuPulse looks like this in a channel. It sits on the bottom, has a 3-beam design, so better velocity coverage. For those of you that are familiar with the older ADFM Pro 20, which was a 4th sensor, this 3-beam design actually does better coverage than that design. And it's also specified 2% flow accuracy. So you have excellent accuracy, and it will handle some other conditions that the older style did not. This is some of the diagnostic without getting into great detail. What's key about this is a single reading. I can look at very detailed analysis of that particular point. One of them is signal strength, how well all 3 beams are reading. Correlation is how well they matched, and velocity bends. So if you were to have a billing application, it could go legal, might go to court. This is very defendable data. Closed pipe. So in a collection system, you might have applications where you have a mag flow meter on a pump station and it failed. Well, it's sometimes very difficult, expensive to do a bypass or replace a mag meter. So we sell a lot of these in these types of applications where the hot tap. So what it's going to do is it's going to mount just inside the pipe about 1/8 of an inch, and it will do a velocity profile of a closed pipe system as well. So very accurate, again, 2% device without taking the pipe out and doing any major construction. Pulse Doppler, some of the advantages. In the open channel version, we can go anywhere from 3 minimum to about 5 inches in the large pipe typically, so we need to at least that much. We will be 2% flow accuracy. It's the only device out there that does velocity profiling. People will do manual profiles using a handheld device, but this does it the same way every time, very precise and very accurately. Can handle up to 20 foot of water depth, can be both portable or permanent, and it has a non-drifting upward-looking ultrasonic to measure the level. No calibration is required. Okay, so what are some of the disadvantages? Well, it's mounted on the bottom of the channel, so you have the same debris, potential rags, some damage on CSOs possibly, and you need a little bit of water to work with. As I stated, the 2150 can read down to 1 inch. The Pulse Doppler needs 3 to 5, and it's going to be a little more money up front than the standard continuous wave sensors, and you're going to draw more power. Installation of large pipes, sometimes that can be very, very tricky. due to some of the site conditions that you're dealing with. Okay, so that is a kind of a quick wrap-up of our contact sensors, we call them. Now I'm going to talk about non-contact. Why do we do non-contact? Obviously, safety is a big thing. Maintenance is a big thing. In this picture, nothing is going to read if it's covered and stuff like that. So what Teledyne did, we developed what we call laser flow. And we really think this is a huge part to unlocking the door to a successful monitoring program. So what laser flow does is it is a non-contact laser velocity system, uses a non-contact ultrasonic level measurement, and it also has a continuous wave area velocity sensor, similar to a 2150, that's mounted on the bottom of the laser when the unit goes surcharge. So, theory of operation, this is kind of a side view of what we do. We have an ultrasonic that's in the back, reflects off a deflector plate. We know where the water is. Once we know where the water is, we focus the laser below the surface of the water. That is our patent, and nobody does anything quite like this. So that's one of the unique features of the laser flow. So before we get into laser details, let's talk about how we get our level measurement. The ultrasonic sensor on this, we angled intentionally to prevent moisture from accumulating. So in the design, we looked at other devices in the market and we said, okay, here's some limitations. What can we do to improve when we design ours? And this is one of the areas. We also have a deadband, which is common with any ultrasonic sensor. And so what we've done with this is we've angled the sensor, we mount it in the back, and we shoot off a deflector plate. What that accomplishes is now we've removed our deadband or eliminated it in the body of the sensor itself. So that laser will actually read level all the way up to the bottom of the sensor itself. We have a 10-foot range on this ultrasonic and the laser, so it's got a good span. So how does the laser work? It's kind of like if you took a magnifying glass and you moved it until in the sun until you got the smallest point and it burned your hand. Similar concept with the laser. We will get reflections off of the entire laser beam, but a lot of the stuff that's not in the focal area will be weak and misdirected and won't be used. What we're looking for is the focal point, which is where we get our maximum reflected energy or light signal back to the laser diode. We do a Doppler shift. We transmit a known frequency. We can calculate the Doppler shift from the return signal to calculate that velocity. So it's a similar Doppler concept. So I'll give you another better look at it from looking at the front of it and the side. Theory of operation, we know our depth. Once we know where the water is, we focus the laser below the surface of the water. What's key about this is this converging section where we're looking for the water. We take 5,000 spectrum velocity readings in a matter of 2 seconds. So the laser does incredible amount of stuff in a very short amount of time. This gives you kind of an idea of what we look for. The spectrum on a laser, we see as we get a reading, we scan it again, and every time the reading agrees with each other, we build this peak, or what we call area under the curve. The larger that area under the curve, the more confidence we have in the reading. We trim off the front end, back end, and that is our frequency. The bottom scale on this is really the speed of the water. So if you look at what a laser does now, we've continued to improve on what we start with, and laser's no different. The first lasers could not read as low a velocity as the laser now. If you purchase a laser in the last 2 years, it can read extremely low velocity. The reason is we're looking at our signal to noise ratio. And if you look at this spectrum, the bottom, which is again 0 is 0, to the right is our fastest velocity. This is telling me I have a very distinct signal compared to my noise. As my water slows down, it will shift to the left. We have no noise, we have a very strong signal, so we can read very, very low velocity. This is known as Doppler power, and this is a measurement really of the quality of the reading we're getting back. We have a certain threshold we require, happens to be 1,000. This reading is stored in memory as well. So when you post-process data, I can look at data, you can look at data, you can tell if that laser was reading correctly when you're looking at the readings. So very powerful tool, very useful to do, again, starting up a laser, knowing if it's working, and post-processing data. So how do we set one of these up? We can do a couple different things. One is known as a single point velocity method. We measure the water depth so we know the distance where the water is. Once we know where the water is, we focus the laser below the surface of the water. In a theoretical velocity profile, our peak velocity is below the center in the middle, which is what we're looking for. We take 5,000 readings, and that's our velocity. This is known as a single point velocity method. The laser is very advanced in that it can do multiple things. In other words, it can go left to right. We can scan up to 15 different velocity points when we take a reading. Each one is 5,000. You do the math, that's 75,000 velocity readings in a matter of about 2 minutes. This is known as a multi-point, multi-depth velocity mode. So why would I use one over the other? Power, if I'm using one on batteries, would be a key factor. Is it a billing location? Do I want 1 minute readings, or am I okay with 5 minute readings? Things like that. So what we normally do is turn them all on, and what you'll get is something that looks very similar to this. This is a signature flow meter laser grid. So I can see on the left side of looking at the laser, at the bottom I was about 8.2 feet per second. At the right, I was all the way over to 5 feet per second. So you can see a distinct difference in the velocity distribution. This is one I calculated just the other day, actually, on an inflow of a wastewater plant. What's interesting is you can see by the velocity distribution, we had a very irregular profile. On the upper left, I was 2.49, 4.98 in the middle, and 5.37 in the far right. When we average all that out, our average velocity is 3.8 feet per second. So laser is able to do some pretty incredible stuff when it takes a velocity reading. Okay, so that's great. We have open channel, no problems. What happens when we go underwater? The laser, in this case, was under about 15 feet of water. So what we do is we have a sensor mounted on the bottom. It's a continuous wave Doppler sensor. When we go under, we use that continuous wave sensor to read velocity, but we have a pressure sensor that also reads the depth. So now you will get a very accurate reading all the way up through the water column. There's how our sensor is mounted on the bottom. It can be retrofitted after the fact. You can order it with it, or again after you have one. This is some data from a site where they had a flume that they feel is accurate and left until it surcharges. They used a signature flow meter with a laser and the ultrasonic. So here they use the capability of multi-sensor on 1 meter. The first part of this data, you can see the laser flow versus the flume tracked very close. Once it was submerged, the flume actually overflowed the sidewalls, underestimated the flow, but when it came back down from being submerged, you can see that the laser in red had a lower flow than what was in the flume. It took about 5 days for the flume to come back into reality of where it should have been. So we designed the laser for collection systems. Large pipe, we define as anything typically larger than 36, and small as anything less than 36. Okay, so we've compared a lot of different devices in the marketplace. One is a Multipath transit time, and this is one that people feel can be very accurate, normally a 2% device when things are working well. In this case, the transit time was within 2%, or the laser was within 2% of the transit time. So we did very well there on that one. Acoustic Doppler, again, range-gated Doppler. So in this case, we ran a laser against an active pulse and a 72-inch line. They both did extremely well. The bottom line is the flow, bottom pane is the flow, blue is the active pulse, red is the laser. So what does this mean? Well, if you have a good hydraulic profile, it tells you that the laser will work very well in those types of applications. If you have billing or it could go legal, you might choose to use the active pulse. Installation in front of flumes. Again, we have more and more people questioning the accuracy of the flume. They're using laser to verify that. And again, they can tie that in with a signature to see how well it's going to work. Flumes have been around since forever and are widely respected in the industry as a 5% device. This is a test we did where we found that the laser was well within the flume measurement. Low level, high velocity. This is another challenging application, and the laser will read down to 1/2 inch for velocity, and we can read up to 15 feet per second. So this was a site where they tried to monitor in the past using a standard in-pipe sensor. The water hits it, goes everywhere. It was not going to work. So they chose laser. This one is a pretty good example of a contact sensor. And if you can see up into that pipe a little bit, they had a good profile until the last two pipe joints, and then everything kind of went a little haywire. They're going to have errors in both their level and their velocity reading, and then unfortunately cables will come loose from the ring, and you're going to catch debris, or you could catch debris pulling that thing out or causing a damage, so dam effect. The laser can be pointed both into the flow or downstream. It doesn't care which direction. The tabs that you see on the top are designed so that you can do a pull retrieval if you want to pull it out without going into the manhole. So if you ever had to pull it out to clean the pipe or do anything, you can remove it, do your maintenance on the system, put the laser back in place. It does not lose its calibration. Flow velocity. Again, this is one of the key things that I'm seeing more and more of, is trying to measure things like personal property INI and stuff with a velocity is very, very slow. You'll have debris settle out on a standard in-pipe sensor. The laser can read extremely low velocity. In this case, our velocity was 0.39 feet per second at the point where I was at. Our spec is a half foot per second. You can see in this case, and we don't guarantee this on everyone, but in this particular case, we were down in the 0.3 foot per second range. Unbelievably low velocity. Here's what I call extreme monitoring location. This dash line at the top is below 1 inch of flow. Okay, so we're down into the very, very low end, but the velocity is anywhere from 2 to 6 feet per second. Extremely difficult application. When you look at this data, you can see though that our Doppler power was still 2912. As I told you earlier, it needs to be greater than 1,000. So when I look at this, I am confident that the reading I'm getting, despite the fact that it's less than 1 gallon a minute, is in fact accurate and valid. So incredible what this thing is capable of doing. So we had another application challenge. I have a drop pipe. We see a lot of these in the industry. How are we going to measure that? These guys did not want to put a ring in the pipe. So what we did is we adapted the laser to be able to work in this location. A standard laser would have a level reading right below it, and it would be reading velocity below the pipe. The new laser, or the one of the models you can order, now has a removable ultrasonic that mounts up in the pipe, so it now reads level and velocity in the same location. It's going to do two things for us: be able to adapt for elevated discharge, also improve our performance and accuracy, because we're truly reading both level and velocity in the exact same location. Here's kind of a good shot of one that was a CSO outfall in Omaha. You can see the level normally would have read there, and it would have read the wrong spot for velocity. Now we have the ultrasonic in there. We know we're getting the exact right velocity point. Here's one very, very shallow line. Nothing that I know of in the industry will read lower level, smaller pipe flows than the laser. However, in this case, they had a grouted pipe that was making it very challenging. They had less than 1 inch of water, and you could see it was kind of free falling into it. So we made some modifications to some of the firmware, and we have a thing called adaptive focus, which is almost like an autofocus of a camera. It knows where the water is, it knows where it wants to get the reading, but if we turn this on, it will actually automatically scan, look for the best reading, lock in on it, and take 5,000 velocity points at that reading. So it has now become very, very intelligent. Okay, we had another, we're seeing more and more wastewater treatment plant influent applications. They want to measure something like this. So there's a rotating bar screen, and they said that level changes 3 inches in a matter of 1 minute. So how will the laser work? We didn't really know, to be honest, so we went ahead and set one out there. They put it in, and it did extremely well. They did a fill test at a clarifier, which is a bucket stopwatch. They went ahead, they timed how long it took to fill, and they calculated their volume. The laser in every test they did, which they did multiple 3 times, was within 2%. They also compared to the influent magmeter, which was in 1.3% of their mag flow meter, so it did very, very well. And here's the data from that site. So you can see it looks very fuzzy, but the screen would plug, rotate, and then water would be allowed to flow. So influent wastewater plants, we're seeing a huge surge of activity using laser for that. Pump station flows. We have cases where people try to measure pump flow. In this case, the level goes from 0 to 10 inches on the bottom pane there, and literally at a snap of a finger, velocity 0 to 6.5 feet per second, and the flow rate as well from nothing to a raging torrent of flow. They had a mag flow meter. In this case, it was reading 9.2 million gallons for this total flow period. Laser tracked well within the spec at 9.3, so they were very impressed with that. So stormwater, more and more applications related to stormwater. Stormwater, we all know, has debris issues, things like that as well. We can mount the laser easily in a storm application. There's a couple gentlemen installing them, and they got creative and just used some C-clamps to clamp that thing in. Another site, this is a signature meter with a sampler. They have a laser on this one, but they have a couple other sites where they have primary devices, so they have bubblers in there, but a nice system there. This is what it looks like when it's installed. This water was crystal clear and less than an inch deep. We were reading this down to less than 10 gallons a minute flow very reliably, so did really well in that application. Okay, wrapping up laser Doppler. Advantage, obviously non-contact, 5,000 readings in 2 seconds. It does an amazing amount of stuff in a very short amount of time. Multi-point velocity readings. Nobody does multi-point subsurface velocity readings. Laser's the only one that can do that. We can handle both large, small pipes. We have them in 6-inch pipes, as well as huge channels. 4% flow accuracy. We can handle anywhere from 1/2 inch to 120 inches with no decrease in accuracy. It's the lowest velocity measurement of anything I'm aware of. Our spec is less than 1/2 foot per second, but in some cases you'll get much lower than that. Portable or permanent, and a non-drifting ultrasonic. Disadvantage, I'll have to point out some, not very many, but it is more expensive than a continuous wave. On the upside, it's less expensive than pulse Doppler or maybe some of the transit time meters or some of the other ones you might be aware of out there. Takes a little bit more power than a standard 2150 for you 2150 users out there. So DC applications, you may want to make sure you have enough power. Depending on what you have a huge foam, fog application, a lot of steam, may not be your best choice. Okay, let's talk equipment options. What do you have for power? AC, DC, what are your meter choices? You can go permanent, signature, or portable signature as well. You can also go 2160. So if I have one that's going to be out there, manhole could flood, I'll probably go with the blue box. Let's talk about how we're going to get this data. Now we have all this wonderful stuff. Let's get this data back to us. We developed Flowlink Pro and Global software. What that did initially was give us unlimited database size, but it allowed us to push data into the server. Instead of calling a site, downloading, it now pushes data to you, so you have easy access, and you can have multiple sites out there transmitting data almost simultaneously and getting that data to you. It's a very efficient way of moving data. We have incredible alarming output capability as well. So when we're getting into more and more industrial monitoring, people are wanting the data transmitted to a central database. That way the industry doesn't have to mess with it. The meter's out there doing its thing, takes readings, stores, and transmits. If there's an alarm based on pH or flow, they will get an immediate notification, and it allows them to immediately not only get an alarm on their phone, but they can view it on anything that has internet connection. So now they can pull out their iPhone or Droid and go, wow, I have a pH violation at my facility. What's going on here? And one of the other key things is we allow you to own your own data. So when you own Flowlink Pro, you own your data. The only thing you pay for is your monthly service charge to a phone company based on your cell service, and that's between you and them. But normally it's anywhere from $8 to $10 a month. So a very good way of moving data. So let's give you kind of a picture view of what this thing does. We have the signature, or we have 2100. They're in the field taking readings. They transmit through the internet. We go to a central database, which could be SQL Server or Oracle. Multiple people internally can view the data via Flowlink client. Off-site, you can VPN into your server and view the data. Or again, with Flowlink Global, you're able to pull up data on your phone and see what's going on, or your computer. Some of the antenna options, and here's kind of a very creative one. This is one in Colorado where they actually cored a little recessed point in their manhole lid, and this is an antenna that just mounts right to it. Snowplows are not going to be a problem with this one. We have different styles of whip antennas. Here's one that we had. We'll stick to the inside of a manhole ring. Again, another one, this is a manhole antenna that would be not recessed in, but bolted right to the antenna, to the manhole lid. And you can even do some things like this, which is a blade antenna. We just epoxy that to the surface of the manhole lid. Flowlink Global looks like this. By the way, we'd be happy to supply you with an IP address. If you want to look at Flowlink Global, send us your, just send an email to us, and we'll give you an IP address where you can kind of take a little tour in that. You log in, though, and the immediate thing it does is allows you to take a quick view of what's going on in your system. So when I pull up Flowlink Global on my phone or on my computer in my office, I can see green is good, yellow means it didn't call in, red means I have a hard alarm. So I know exactly what's going on at a quick glance in my system. It also allows you, as a one click, to be able to graph your data. So now I click on, with one touch of the mouse, I can see exactly what I want to see, my level of velocity flow rate. I also have GIS mapping capability, so I can pull up a map view and see where I have alarms, as well as being able to deploy my crews more efficiently and effectively. Okay, so again, flexibility on some of this stuff. We talked about the smart device, which again is signature. So you can use up to 9 different smart devices on that. So let's recap some of the applications where we might use some things. So capacity assessment or hydraulic modeling. That really comes down to, people will call us, what do you recommend? Well, it comes down to, what are your pipe sizes? What are your requirements? You may have large interceptor lines. In that case, you either go with a active pulse, or you maybe have a large interceptor line that has very low flow most of the time. You might want to go laser, or you have high flow and you can't get in there. You want to go laser. INI studies. 2150s are the workhorse of the industries on that, which is continuous wave Doppler. And again, those are used. They're very portable, easy to move around. Having said that, if you have applications where you have low levels, very shallow flow, you may want to use a laser. Again, laser will read below an inch. That's the only device in the market that will read below an inch. Pump stations. How are we going to measure those flows? Probably use something like a hot tap. Then we go SSO. SSO, again, we're just trying to find out if we had an overflow condition. We can use a 2110 ultrasonic that is a level-only device connected to one of our cell modems, can give you immediate notification that you had an SSO event, as well as allowing you to pull up the data on your phone. Industrial dischargers. We're seeing more and more municipalities using Flowlink Pro and Global as their main database platform. When they have signature involved, now they can choose what device they want. So some industries already have flumes, but they have brand Z meter, and it doesn't make sense. They'll go ahead and they'll use signatures on those industries, and they'll say, okay, you have a flume that works, use a signature bubbler or ultrasonic. If you don't have a primary device, you might go laser, or you might go standard area velocity. But all of it's being moved to a central database for immediate notification. This helps both the industry and the municipality. CSOs, large pipes in a lot of cases, very low flow. What are you going to use to measure that? Laser is a really good choice because combined sewers in a lot of cases are going to have some severe debris potential due to God only knows what's coming down the line. So CSOs, you can use ADFMs or pulse Doppler. You can use really any of the devices we manufacture. And then finally, we get the water to the wastewater treatment plant. In this case, we can use signature lasers on the influent of the plant. We can also use hot taps in the plant. We can use pulse Doppler. We can measure the influent or effluent, and using, again, laser or a variety of different types of measurement technologies. So in summary, Teledyne ISCO really has a complete flow solution for just about every application. Signature is unmatched in its flexibility, and we can really assess your site, your requirements, and we can adapt to those very easily. The new AccuPulse is very exciting. It's one of the most accurate, probably the most accurate open channel device on the market. Again, specified 2% for both small or large pipe applications. Laser flow, really amazing device, most advanced, versatile, open channel, non-contact device that we're aware of at this time. And it works in applications that previously people thought were unmeasurable. Low level, high velocity, slow velocity, very clean water, and so on. So amazing technology. And when you have that kind of technology, the internet connection really ties it all together. We're able to bring it all in, and now we have a complete solution. Flowlink Global is going to allow you to have data access anywhere, anytime in the world. And at that point, I'm going to go ahead and leave it up to some questions to my associate, Bill Soulier.
Okay, Rick, we got a couple of quick questions came in during the presentation. One of the questions was, will a laser flow work on a small pipe application?
Okay. And the answer to that is absolutely. We're shooting a laser beam into the flow, but the ultrasonic is one thing that people will get hooked up on sometimes. They think, well, the beam width is spreading, and that's true, it does. But we're able to dial in that the range of where we're looking for a level. So we can say, don't look any further than this 2 feet, and don't look any closer than 1 foot. So we can specify for the ultrasonic exactly where we want to look. But the laser beam itself needs, just a very small opening to read. So the smallest I'm aware of that we've done is 6, but I'm sure we can go much lower than that.
Okay, you mentioned a signature flow meter is available in portable or a permanent mount. When you go portable with the signature meter, what type of power source do you use?
Okay, that's a good question. The signature initially was designed for more permanent applications. Over the last couple of years, we modified it so that it will work in a portable scenario. In that case, it can run off of both AC power or DC. It can run off of your standard ISCO batteries you might use for your samplers. It can also run off of deep cycle marine batteries, solar panel, things as well. The thing that's pretty interesting and neat about the signature is that when you run it in a portable mode, there's really 3 ways to operate it. One, you can run it continuous, so it runs just like a normal signature with the backlight display on, keypad, and the real-time readings. You can also turn off the backlight but still have it go into real-time mode, but it will reduce your power consumption with the backlight off. And then you can even go further than that and have it go into a vlogging mode where it will shut off the backlight and the display and go into a wake up, take a reading, and go back to sleep mode. So a lot of power options available for the signature, and it's, again, designed for battery backup. One thing that I should point out as well is the data being stored in there is downloadable just using a thumb drive, so a USB drive plugs in, downloads the data, so you can get your reports and everything right off of that as well. And we also have software that will analyze that data that you downloaded and verify that it was, if it was modified in any way, it will flag it as non-verifiable. So very solid meter to use, especially for compliance monitoring.
Okay, Rick, we've got the next question coming in. And this has to do with measuring flow in a large pipe. And at certain times, it'll have no flow, and then it'll go to a really slow, shallow flow. But then in a really rain scenario, then it'll get very high flows and very fast. What type of technology really applies to an application that can handle all of those flow scenarios?
Okay, good question. In the old days, we really tied in a couple of different technologies. We'd use a continuous wave Doppler like a 2150, and we would use a pulse Doppler to handle the large flow, or the deep flow. And that worked okay, but that was still sensors on the bottom. The laser, if you can't tell, I'm excited about laser, but the laser doesn't care if it's low flow, doesn't care if it's shallow, slow, and it can handle, again, a large pipe, very low-level stuff, and then when that flow kicks in, it will take and handle that all the way through the range as well. So the laser would be the one that would be the best choice in that scenario.
The next question has to do with portable equipment that can be easily installed and removed, and, the maximum monitoring period is maybe 1 to 30 days. For a scenario like that, what type of flow measurement technology would you recommend?
Okay, so a quick monitoring project depends a lot on pipe size, really. 2150s are pretty hard to beat, which is our area velocity, the continuous wave area velocity blue box units. For that reason, because it's easy to go in, all they have to do is really set the level to 0, insert the ring, double check their level, make sure it's accurate, and it's going to take off and do its thing. It's easy to pull that out, and away you go to the next one. If you have larger pipes that maybe you want to come back to periodically, we have customers that will either use a portable laser jack mount, and they'll just insert it, go in, they'll insert it, but they're not in the flow. Or some will actually mount laser permanent mounts in those locations that they may come back to. The nice thing about that is they don't have to necessarily have a laser for each site. They can use a handful of lasers, move them from location to location, reinstall them, and with the way the programming goes, you can clone the meter so that it knows it's back at site 2, and it will program itself back up to exactly the pipe sizes with the data storage interval, and you really don't lose anything in that, and all you have to do is calibrate level. So it depends on pipe size and applications.
Next question has to do with the laser flow, and asks how far away can the laser flow be installed from the sensor, and have we ever used it in under bridge applications where we're trying to monitor maybe river flow or something like that?
Okay. The standard distance is 180 feet, and we can go longer if we parallel the wires. Okay, so we can parallel the power supply or power out locally from the electronics unit. And we do have people using them under bridge for canal stuff and looking at more river monitoring. I have a couple that are at the influent of a water drinking plant that they're looking at measuring about 20-foot wide channel. In that case, they said, how many lasers do I need? Well, if your flow is uniform, you can use 1. In this case, you might want to use 2 because you got a pretty wide channel there. And so they use 2 of those. They're mounted above the water, but you can mount them underneath bridges as well. We see a lot more irrigation water type applications coming down the road using laser as well. Good questions out there?
In addition to that question, from the bottom of the sensor, on the laser flow sensor, to the surface of the water, what's the maximum distance there?
To the bottom of the laser sensor, to the minimum depth is 10 feet. So if you have, if you're in a 10-foot pipe and it's dry, you're fine. If you're in a 12-foot pipe and you have 2 feet of water minimum, then you can mount it there. If you have a 12-foot pipe and it's dry, then you might have to mount it down in a little bit lower in order to cover that range. Or in some cases, people will use a continuous wave like a 2150 or a 350 sensor, and they'll just tie that, they'll put that on the bottom. That'll read the level up to the 2-foot, 3-foot range until it's in the range of where the laser level and laser can read. One thing to note about that, the calibration of the laser is really nice because it tells you where the water is. So the distance from the bottom of the laser to the water surface is known by the laser. When you calibrate one of these, a lot of times it's difficult to get a ruler measurement in there. You can just measure the bottom of the channel to the bottom of the laser and subtract the measured distance on the laser, and it'll tell you exactly what your water level is. This allows you to do a much better job calibrating the level to begin with, as well as verifying your level after the fact. Anytime down the road, you can verify that. So, very, very flexible that way.
In an earlier slide, you showed a software package that had a GIS element to it, and I think it was Flowlink Global. Could you explain a little bit more about the GIS element and the advantages of that?
Okay. When we came out with Global, we wanted somebody to be able, or the customer to be able to have access to their data remotely off of any type of web browser. When we looked at that, we said, okay, we want to be able to graph the data, but we also wanted to give them the ability to easily see what's going on in their system, and that involved a GIS mapping element. So when you set up the meter in the field, all you have to do is on the meter, you tell it its GIS coordinates, and it automatically populates this in Flowlink Global. So when you set Global up, you can set it up to do a number of different things. One is the dashboard view, which I kind of like because it gives them a quick view of what's happening in my system. Having said that, you could also set up that to be as default as a GIS map. If I have a number of meters out there and a number of crews, you could set each crew up with their own password, their own login, and then when they log in, they'll see immediately what's going on in their basin. They won't necessarily be able to see the other one. So that's a really nice thing. It also works well if you're a flow service company out there and you're monitoring different or doing different projects for multiple municipalities. You can set up a login for each municipality. They log in, they can see only their data, and you can keep track very easily of what's happening in the different studies that you're doing as a flow service provider. Okay, I think that's about it for questions. If you have multiple questions or other additional questions, please let us know. You can email me at rick.dey@teledyne.com. Or we welcome you to come by if people are going to the West Collection System Conference. It's in Atlanta here in about another week and a half. May 2nd and 3rd, we'll be there. We'll have all of our stuff to show you and be happy to answer any questions that you have. Again, this was a record number of people this time, and appreciate everybody hanging in there and listening to me. If you've listened to me again for a second or multiple times, appreciate that. And you new listeners out there, hopefully this was useful for you. Again, thank you. I look forward to seeing you in Atlanta.